Hi, my name is Birdie Juarez, and this is my final presentation for the Mechanical Behavior of Materials project. My project was a structural analysis of a rotomolded polymer pallet. This is something that we manufacture at my workplace, so I thought it'd make a great project. My objective in this project was to conduct a structural analysis on some of these pallets and find the maximum deflections. After that, I wanted to compare these to our real compression testing data and perform a model convergence exercise. So we do a lot of compression testing of these pallets to see how strong they're really going to be and what loads they can actually hold before we sell them. So I have a lot of data to compare to, and I really wanted to get my analysis to be as close to the real world data that we have as possible. My goals were to conduct the analysis using various loads, loading areas, and material properties. Part of that was to get a result that was close to real world, and the other part of that was because we do use different loads when we're testing. We use different loading areas, and there was a bit of a hiccup with some material properties that I wanted to investigate. So that was pretty important. The second goal was to perform an analysis on a pallet that has steel reinforcements. So I knew that that would allow me to use ANSYS contact features and the multiple bodies and just see if I could get an analysis that actually made sense. The third goal was to perform an analysis on one of our pallets that is ribbed and see what the difference would be if we were to remove those ribs and just have a flat top pallet, how much strength loss would occur. So those were the three biggest goals that I had. I have three models. The first model is the D525. This is one of our smaller pallets. This is the one that I wanted to do the smaller tests with, such as the variable loads, loading areas, and variable material properties. The D545 is one of the pallets that we have standard right now, and that is the ribbed top as you see in these images. And the D546 is the same pallet design with just a flat top, so everything else remains the same, all the dimensions are the same. And both of these pallets have steel reinforcements, whereas the D525 does not. So I knew that the D525 would be easier to do the quick tests with. So for my boundary conditions, these were pretty much the same for all of the pallets except that the loading area did change. I did an offset load to one side and it was about half the area of the pallet. The fixed supports were the same for all of my analyses. It was just the bottom surfaces of all the legs. And the mesh for the D525, which is what you see here, was a little bit large. It was not really complicated. I did a lot of cleaning of the model itself and removing a lot of the fillets that were not going to affect the strength of the pallet. And I just wanted to get the analysis to run a little bit faster. So I didn't use a really complex mesh on the D525, which is the one without steel. I did get the chance to check and see if my fillets were going to be critical or not, and you see in these images it's very clear on the right side, which is the stress plots, that the fillets near the legs on the inside where the brightest colors are actually pretty critical because you can see that there's more stress concentration happening there. On the left, these are the deformation plots, so that's the half area offset and then the full area load. So you can kind of get an idea of what the deformation would be. And these were done with various loads, so I did 1,400 kilograms and then 2,300 kilograms, so we'll get back to that in a second. I was not getting close to my real-world data, so I started looking at my material properties. After I edited the mesh and the models and everything else that I could, I realized that our material properties may have been having the most effect. So the published properties from the actual polymer manufacturer that we use had a flexural modulus of 603 megapascals. So we also had data from the guys who buy this polymer and then distribute it to us. So our distributors had data that did not match the manufacturer's published data. So their stress strain tests that they did, we had actual data sheets with all of their stress strain curves, and I did a quick analysis to find the slope, and I found that that was 285 megapascals. So that is quite a bit weaker and would have a lot more deflection. It's not an insignificant amount, so that was a little bit troubling, but I wasn't convinced that our actual polymer was that weak, and so I don't know if they sent us the wrong data. They sent this twice, so I'm not sure what was going on there, but I went ahead and did analysis with this to see what that would come up with. So on top you see the published properties, which is giving us a deflection of about 9 millimeters, and then the distributor's incorrect data that they sent, which would give us way more than double that. So that would be very bad, and that's not something we want. So that is not what we were seeing in real life. We were actually seeing quite a bit less deformation than this in both cases. So there was still something wrong with my models or my analysis using the published properties. But it is pretty interesting to see the difference of what just the modulus can do in your analysis. So here's a video of the pallet with the Dow properties, which was the 600 megapascals, and you can see the 9 millimeter deflection happening. And then there is the distributor's data, which had a much lower modulus, and you can see the pallet does deform quite a bit more. This is pretty interesting because when our pallets are in the compression tester, they really do tend to deform like this. So I was happy to see that it really was looking the way it does when we test in real life. So that brought me to our manufacturer. I wanted to get data straight from them. I wanted the raw data from them, so I jumped through a few hoops and got data from the actual polymer manufacturer. And this data was right off the bat clearly more detailed. They had a lot more test points and a lot more tests that they ran. And I then compared that to their published secant modulus, which was a 1% secant modulus. So I took the same one, and that came up with 970 megapascals, which is much higher than their published properties. And thank you, Dr. Zhang, for helping me with that, because I did not know how to take the secant modulus before this time. So that was very helpful. But yes, this is quite a bit higher than what we had in the published documents. So I went ahead and tested with that, and it turns out that my test actually got much closer to reality that way. So the polymer that we order is supposedly a medium density polyethylene, but that modulus matches better with a high density polyethylene. So I'm not sure if we are getting a higher density polyethylene than we thought we were, or really what's going on there, but it did make my analysis match much closer to reality, and it really wouldn't be that much of a surprise. We're not real picky about our polyethylene. It does need to be strong enough, but it being a little bit higher density would not be troublesome, but being lower density, the 285 megapascals matched closer with like a linear low density polyethylene, and that is not something we would want to manufacture these pallets out of. So here I was getting a deflection of about 3.1 millimeters in my analysis, and our real-world testing data of the same pallet under the same loading conditions was about 2.7 millimeters, so that is pretty good. I was happy with that. This was under 1,400 kilograms. I ran it again with 2,300 kilograms, and I also got a good result. My analysis came out with 5.2 millimeter deflection, and our compression testing data had 5.2 or 5.02 millimeters. So there is a bit of a difference, but not bad at all. I was really happy with that. So that brought me to the D545 and D546 steel reinforced pallets. Now that I knew I could validate a simulation I wanted to validate the D545 and then go ahead and remove the ribs and test it again on the flat top version and compare the strength. So the ribs add a lot of strength to our pallets and they're pretty important, but certain customers want flat top pallets for their shipping purposes, and manufacturing one of these is a little bit tricky, so we don't want to lose any strength when we do that, but it's kind of inevitable. So we just want to know how much that would be. Making a mold for these pallets is about $50,000 to $100,000 depending on how complex the model is. And so it's not a small investment, and we kind of want to know before we get into it, are we losing too much strength that it's not even worth it? So this was a very good exercise that I really enjoyed. The mesh for these, I spent a little bit more time on. I did a much more complex mesh boundaries here, or whatever you want to call it. I spent a lot of time on it. So I used a much smaller mesh. I kind of went out and investigated in the warehouse to see, was the steel really perfectly bonded to the polymer? Was that appropriate to use for my mesh? And, some of the engineers said, yes, you can just consider it perfectly bonded. The steel is not going to move. And then, our warehouse guys who work with these pallets every day said, no, you can hear the steel moving around. If you load the pallet, the steel doesn't move the same way. So I ended up going with a rough contact because I figured the polymer does move around the steel a little bit. It's not completely stuck together, and if you load the pallet, it's probably going to move a little bit. So this really, really increased the complexity of the simulations. Doing a rough contact takes a lot more time, and it's a lot more solving involved. So that took over an hour to run any one of these simulations with the rough contact. So that came up with a 1.2 millimeter deflection. That was a full area under 2,500 kilograms, and this I then compared to the flat top pallet, and that came up with 4 millimeters. So that's a big difference, but it does kind of give us an idea of what would be the result of removing the ribs. So when I did this, I compared my simulation for the rib top to real life, and in real life we're getting about 1/4 millimeter of deflection under the same loading conditions. So there is a big difference there, and doesn't make my simulation quite trustworthy. However, after talking to the engineer who does our testing, I discovered, here you can see our actual results. There's a 1/4 millimeter circled in red there. But I discovered that he actually places the strain gauge, in this case, close to the center leg. And I'm not sure why. I think it has something to do with the steel frame. He said that's where he puts it. And when you actually look at my deformation plot on my simulation, you see that it fits relatively well with that. It's somewhere in the 0.1 to 0.4 millimeter range if you place it where he puts his strain gauge. So that fits a little bit better with what he was getting from his actual compression testing, and that made me very happy. So we can trust this flat top pallet simulation a little bit better knowing that. And I did spend quite a bit of time editing the meshes and editing the boundary conditions and getting everything right, so that was very nice to see. Finally, I wanted to talk a little bit about why our tests do not always reflect reality. So in our standard compression test, and like in my simulations, I fix the bottom surfaces of the legs. And so I can reflect one of our simulations in the compression tester where it's just a flat area load. But in real usage, and when we put something in between the compression tester to get a better idea of what's really going to happen when they load it with an uneven load, you see that the legs actually lift up and the deflection increases. So the legs are not fixed in reality when customers are actually using our pallets. So that's something to think about for future simulations. My conclusions are that the model convergence exercise was successful. My results were within 5 to 15% of the actual testing data values, so that was really good. I spent a bit of time getting it closer and closer, and I'm pretty happy with where I ended up. The D545 design change to a flat top is awaiting approval, and as far as future work, I think simulating creep and just trying to reflect more real-life loads would be pretty interesting moving on. Thanks for watching.